The universe is a vast and mysterious place that has been the subject of human curiosity for thousands of years. From the ancient Greeks to modern astrophysicists, we have been searching for answers to the biggest questions about our cosmos. What is the universe made of? How did it begin? And what is its ultimate fate? The answers to these questions have come through a combination of observation, experimentation, and theoretical models, which have shaped our understanding of the universe and our place within it. With the latest theories and observations, we'll explore the mysteries of this vast expanse of space and delve into the secrets it holds. Have you ever looked at the sky and wondered why anything exists at all? There are approximately 200 billion trillion stars in the known universe. Or, to put it another way, 200 sextillions. The number is so big, it's hard to imagine. But hundreds of years back we didn't even know all these things existed. Stories of our cosmos have been debated for centuries and can even be traced back even to the 2nd century. Let's take a brief history. In ancient Greece, philosophers such as Anaximander and Aristarchus made early attempts to understand the universe. Anaximander believed that air was the primary substance that held the universe together. He believed that air was infinite and divine. Anaximander postulated eternal motion, along with the Apeiron, as the originating cause of the world. The Apeiron was infinite and could not be created or destroyed. While Aristarchus believed that the sun was at the center of the universe and that the earth and other celestial bodies revolved around it. However, these early theories were not widely accepted. It wasn't until the work of Ptolemy in the 2nd century that the idea of a geocentric universe, with the Earth at the center, became dominant. This theory held sway for over 1,000 years until it was challenged by the Polish astronomer Nicolaus Copernicus in the 16th century. Copernicus argued that the sun was indeed at the center of the universe and that the Earth and other planets revolved around it, a concept popularly known as heliocentrism. This idea was further developed and refined by the German mathematician and astronomer Johannes Kepler and the Italian physicist and astronomer Galileo Galilei. However, their work was met with resistance from the Catholic Church, which saw it as a threat to the long-held belief in a geocentric universe. Despite this opposition, the evidence in support of heliocentrism continued to mount, and by the 17th century, it had become the dominant model of the universe. This was cemented by the work of the English physicist and mathematician Isaac Newton, who developed the laws of motion and gravity. Newton published one of the most celebrated works of science, the Principia, in 1687. In it, he described that the force that pulls objects toward the ground is the very same force that underlies the motion of the planets and stars. Newton formulated this insight into a mathematical equation, known as the law of universal gravitation. When combined with knowledge of geometry and Newton's other equations of motion, we can use them to make predictions about the movement of the planets, the paths of comets, or how much force is needed to get a rocket to the moon. We acknowledge Newton not just because of his idea, but because he was able to formulate his idea into an equation that made predictions with greater accuracy than ever before. But it wasn't perfect. He didn't describe how gravity works the way it does. Newton was well aware of this when he said, "Gravity must be caused by an agent acting consistently according to certain laws, but whether this agent be material or immaterial, I have left to the consideration of my readers." The concept of a heliocentric universe dominated scientific thinking for the next few centuries, until the development of the theory of general relativity by Albert Einstein in the early 20th century, which provided a new and more complete understanding of the nature of the universe. Before Einstein, the prevailing view was that space and time were separate entities, absolute and unchanging, with objects moving through them. Einstein proposed that space and time were intertwined and could be affected by the presence of matter and energy, forming a four-dimensional fabric known as space-time. Space, in its simplest form, refers to the physical space that surrounds us. It is the three-dimensional area that we can move around in and experience. This physical space is often referred to as Euclidean space and is thought of as an absolute and unchanging backdrop to our existence. Time, on the other hand, is a little more complex. Time is the progression of events or memory in the frame of space. It's also thought of as a dimension, just like the dimensions of space. However, time is different from the physical dimensions of space because it has a directional aspect. Time only moves forward, and this flow of time is referred to as the arrow of time. So while time and space are separate concepts, they are closely related and can be thought of as intertwined aspects of the universe. Time provides a record of the events that occur in space, while space provides the stage on which those events take place. According to general relativity, massive objects like stars and planets cause space-time to curve, leading to the phenomenon of gravity. This theory revolutionized how we think about gravity, replacing Isaac Newton's concept of gravity as a force with the idea that massive objects simply follow the curves in space-time. Einstein's theory showed that time can be relative, meaning that time can pass at different rates for two observers depending on their relative velocity and proximity to massive objects. This idea was confirmed by experiments and has significant consequences for our understanding of the universe, such as the possibility of time travel. In summary, Einstein's theory of general relativity refined our understanding of space, time, and gravity, and paved the way for many advances in modern astrophysics and cosmology. Back in his days, almost every astronomer believed that the universe was static, but not until American astronomer Edwin Hubble presented his evidence of the expansion of the universe. Einstein embraced the idea. He called his adherence to the old idea his greatest blunder. Albert Einstein was supposedly elated to hear of Hubble's work. Einstein's theory of relativity implied that the universe must either be expanding or contracting. Einstein himself, however, had rejected this notion. Instead, he favored the accepted idea that the universe was stationary and had always existed. Hubble was among the first to recognize that there are other galaxies beyond the boundaries of our Milky Way. He used a technique pioneered by Henrietta Leavitt to measure distances to remote objects in the sky. Hubble used spectroscopic redshift data to measure the speeds these objects were traveling and then graphed their distance from Earth against their speed. He discovered that the speed at which astronomical objects move apart is proportional to their distance from each other. In other words, the farther away objects are from Earth, the faster they are moving away from us. This became known as Hubble's law. Edwin Hubble observed stars in a hazy patch of light that at the time was known as the Andromeda Nebula. Specifically, Hubble observed variable stars, those that change in brightness. He measured the period of how long a star took to dim and brighten. From the period of brightening, he calculated the star's intrinsic brightness. From that, he could calculate the distance. That's when he realized that the stars in this nebula were so far away that it couldn't exist within our own galaxy. At the time, many astronomers believed that the Andromeda Nebula was a forming solar system within the Milky Way. Hubble showed that this patch of light was really a separate galaxy. Thanks to Hubble, we know it today as the Andromeda Galaxy. It is the nearest large spiral galaxy beyond the Milky Way. Hubble showed there are separate galaxies beyond our Milky Way, and the more distant the galaxy, the faster it moves away from us. These discoveries from Hubble, Einstein, and other great scientists have greatly contributed to our current understanding of cosmology. Their observations and theories have been incorporated into the lambda cold dark matter model, which is currently the most widely accepted cosmological model. Central to it all is the Big Bang. The basics of the theory are fairly simple. In short, the Big Bang hypothesis states that all of the current and past matter in the universe came into existence at the same time, roughly 13.8 billion years ago. At this time, all matter was compacted into a very small ball with infinite density and intense heat called a singularity. Suddenly, singularity began expanding, and the universe as we know it began. The earliest indications of the Big Bang occurred as a result of deep space observations conducted in the early 20th century. In 1912, American astronomer Vesto Slipher conducted a series of observations of spiral galaxies, which were believed to be nebulae at that time, and measured their Doppler redshift. In almost all cases, the spiral galaxies were observed to be moving away from our own. In 1922, Russian cosmologist Alexander Friedmann developed what is known as the Friedmann equations, which were derived from Einstein's equations for general relativity. Contrary to Einstein's advocating at the time with his cosmological constant, Friedmann's work showed that the universe was likely in a state of expansion. In 1924, Edwin Hubble's measurement of the great distance to the nearest spiral nebula showed that these systems were indeed other galaxies. At the same time, Hubble began developing a series of distance indicators using the 100-inch Hooker telescope at Mount Wilson Observatory. And then in 1927, Georges Lemaitre, a Belgian physicist and Roman Catholic priest, independently derived the same results as Friedmann's equations and proposed that the inferred recession of the galaxies was due to the expansion of the universe. In 1931, he took this further, suggesting that the current expansion of the universe meant that the farther back in time one went, the smaller the universe would be. At some point in the past, he argued, the entire mass of the universe would have been concentrated into a single point from which the very fabric of space and time originated. These discoveries triggered a debate between physicists throughout the 1920s and 30s, with the majority advocating that the universe was in a steady state. In this model, new matter is continuously created as the universe expands, thus preserving the uniformity and density of matter over time. Among these scientists, the idea of a Big Bang seemed more theological than scientific, and accusations of bias were made against Lemaitre based on his religious background. Other theories were advocated during this time as well, such as the Milne model and the oscillatory universe model. Both of these theories were based on Einstein's theory of general relativity and held that the universe follows infinite, or indefinite self-sustaining cycles. After World War II, the debate came to a head between proponents of the steady-state model and proponents of the Big Bang theory, which was growing in popularity. Ironically, it was Hall who coined the phrase Big Bang during a BBC radio broadcast in March 1949. The tide of observational evidence shifted towards the Big Bang theory over the steady-state theory as more discoveries were made. In 1965, the discovery and verification of cosmic microwave background radiation solidified the Big Bang as the prevailing theory of the universe's origin and evolution. This was due to the Big Bang's prediction of uniform background radiation resulting from high temperatures and densities in the distant past. Today, the Big Bang theory is widely accepted due to the abundance of empirical evidence supporting it. Precise measurements of the universe's expansion rate place the Big Bang singularity at approximately 13.787 billion years ago, which is considered the age of the universe. While the Big Bang theory is widely accepted, there are still observed aspects of the universe that remain unexplained by its models. Following the initial expansion, the universe cooled, enabling the formation of subatomic particles and later atoms. The baryon asymmetry, or the unequal abundance of matter and antimatter, that allowed for this is still an unresolved issue. These primordial elements, primarily hydrogen, with some helium and lithium, later combined due to gravity to form early stars and galaxies. In 2014, scientists from the Harvard-Smithsonian Center for Astrophysics studying characteristics of cosmic microwave background radiation detected evidence to support inflation theory. Their observations are believed to reflect the imprint of gravitational waves on the universe in the first few moments after the Big Bang. About 380,000 years after the Big Bang, the universe became transparent to light. For the next several billion years, gravity slowed the expansion of the universe. About 8 billion years after the Big Bang, expansion of the universe began to accelerate. Cosmologists believe that an effect called dark energy is causing the universe to expand by making matter repel other matter. At present, we still don't know what dark energy is, but we'll get back to it later in the video. First, let's see how big the entire universe really is. How far can you see? Everything you can see and everything you could possibly see, right now, assuming your eyes could detect all types of radiations around you, is the observable universe. In terms of visible light, the farthest we can observe originates from the cosmic microwave background, a time 13.8 billion years ago when the universe was dense like a heavy fog. Some neutrinos and gravitational waves that surround us come from even farther out, but humans currently lack the technology to detect them. The featured image showcases the observable universe on a progressively smaller scale, starting with the Earth and Sun at the center, followed by our solar system, nearby stars, nearby galaxies, distant galaxies, filaments of early matter, and the cosmic microwave background. Cosmologists often assume that the observable universe is simply a localized portion of a larger entity referred to as the universe, where the same physical laws apply. However, there are various speculative theories that suggest that even the universe is part of a greater multiverse, where physical constants may vary, different physical laws may be in effect, higher dimensions may exist, or slightly different versions of the standard universe may occur by chance. In the area of the universe that we can see, there are approximately 2 trillion galaxies. The universe is believed to be homogeneous and isotropic, meaning that it looks the same in every direction. As a result, there is no preferred center or edge, and no special direction that is more up or down than any other. The universe simply exists as it is, without a specific center or edge. From anywhere in the observable universe, the farthest point is 46.5 billion light-years away. Of course, that exceeds the age of the universe, which is only about 13.8 billion years, so how is that possible? These two numbers represent different things and should not be confused. The age of the universe is the time that has passed since the Big Bang, while the diameter of the observable universe is the maximum extent of the region we can observe and is determined by the distance that light can travel in that time. Simply enough, due to a process we don't yet understand, the universe is expanding, and the further away an object is, the faster it recedes from the observer. We currently refer to the phenomenon as being driven by dark energy and dark matter, which are terms we created as placeholders until we have an explanation for the process. Dark energy and dark matter are two mysterious and enigmatic substances that scientists believe make up a significant portion of the universe. Although they have not been directly observed, their existence is inferred from their gravitational effects on visible matter. Scientists estimate that dark matter makes up about 27% of the total mass of the universe. One of the ways scientists have tried to detect dark matter is through the use of particle detectors, such as the Large Hadron Collider. However, despite several searches, dark matter has yet to be directly observed. Some scientists believe that dark matter may consist of weakly interacting massive particles, while others think it could be made up of sterile neutrinos or axons. And for dark energy, scientists believe that dark energy makes up about 68% of the total energy of the universe. Although it is one of the most dominant forms of energy in the universe, its nature is still not well understood. One of the ways scientists have tried to understand dark energy is by studying its effects on the expansion of the universe. According to the standard cosmological model, the universe began with the Big Bang and has been expanding ever since. However, observations of supernovae in distant galaxies have shown that the expansion of the universe is actually accelerating, rather than slowing down as previously believed. This acceleration is believed to be caused by the presence of dark energy. There are several theories about the nature of dark energy, including the cosmological constant, quintessence, and phantom energy. The cosmological constant, first proposed by Albert Einstein, is the simplest explanation for dark energy and assumes that it is a constant energy density that is uniformly distributed throughout the universe. Quintessence is a more complex theory that suggests that dark energy is a dynamic field that evolves over time. Phantom energy is a more exotic theory that suggests that dark energy has a negative equation of state, meaning that it increases as the universe expands. As time progresses, dark energy will become increasingly significant, while all other forms of energy, including dark matter, will become insignificant. Despite the possibility of a relationship between dark matter and dark energy, it remains elusive and not clearly understood by physicists with our current knowledge of the natural world. To account for dark matter, an additional component is required that can form clumps through gravitational attraction, but does not collide or apply pressure. Conversely, for dark energy, a component is necessary that doesn't clump or collide but does produce pressure. Are they related? We cannot say for certain. Until we have some evidence that these two things actually are related somehow, we have to take the conservative approach. Dark matter forms and holds together the largest bound structures, but dark energy pushes those individual structures away from one another. The latter is so successful that in 100 billion years or so, all that will be left of our visible universe is the local group of galaxies. Beyond that, there will only be an empty expanse of nothingness, with no other galaxies visible for trillions upon trillions of light-years. As of now, we somehow understand space, time, gravity, light, energy, mass, and other phenomena. But physicists need an equation to show that everything in the universe is linked, a kind of magical equation. The theory of everything, also known as a final theory, is a hypothetical single, coherent, and mathematically elegant explanation of all physical phenomena in the universe. The idea of a theory of everything has captivated scientists, philosophers, and the general public for decades, as it would provide a comprehensive understanding of the universe and answer some of the most fundamental questions about our existence. The current theoretical framework for explaining the physical world is the Standard Model of Particle Physics, which describes the behavior of particles at the smallest scale and the electromagnetic, weak, and strong nuclear forces that govern them. However, the Standard Model does not include gravity, which is described by Einstein's theory of general relativity. The search for a theory that unifies these two models and incorporates quantum mechanics is the central goal of the theory of everything. One of the leading candidates for a theory of everything is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional strings that vibrate at different frequencies. According to string theory, these vibrations determine the properties of particles and the forces between them. String theory also suggests the existence of extra dimensions, which could potentially explain why gravity is so much weaker than the other forces. Another potential candidate is loop quantum gravity, which attempts to reconcile general relativity and quantum mechanics by describing the universe as a network of relationships between discrete building blocks. This theory suggests that space and time are quantized, meaning they are composed of tiny, indivisible units, and that the fabric of space-time is granular. While these theories have gained significant attention and have made remarkable progress, they have not yet been proven and are still being developed and refined. The challenge in finding a theory of everything is that it must explain a wide range of phenomena and be consistent with all experimental data, while also being mathematically simple and elegant. Despite these challenges, the pursuit of a theory of everything is considered one of the greatest intellectual quests of all time. A successful theory would not only provide a comprehensive explanation of the physical universe, but it would also have profound implications for our understanding of the world and our place within it. It would also have far-reaching consequences for fields such as cosmology, astrophysics, and technology. While it may never be fully realized, the pursuit of this goal has led to countless breakthroughs and advancements in our understanding of the universe. Regardless of the outcome, the quest for a final theory will continue to inspire and drive scientific progress for generations to come. What will happen when all the pieces of the puzzle finally fall into place and we understand how our world works? Will that be the end of physics? After we learn the rules of chess, we can finally start playing the game.